We've previously looked at various things that you can do with vectors, such as sliding them around, multiplying them by a scalar, adding them, and subtracting them. In this tutorial, we're going to focus on another thing that you can do with a vector, namely breaking it up into its components. This is by far one of the most useful vector operations that you're going to encounter. And in fact, when you take your physics course, you'll probably literally be doing this several hundred times. Fortunately, it's fairly straightforward. So here's the idea. Let's say I have a vector, I'm going to call it A, and here it is, depicted by this red arrow. This vector has magnitude 7 meters, and it's making a 60-degree angle with the horizontal. So there's vector A. I want to break this vector into xy components. So here's how that's done. The first thing I have to do is draw a coordinate system. So here I've drawn some xy coordinate axes. By the way, as a reminder, you may recall that x hat denotes a unit vector. A unit vector is a vector of length 1 that points along the x direction. So x hat would be a vector of length 1 that points to the right here along the x-axis. Likewise, y hat denotes a unit vector of length 1 that points along the y-axis. Okay, so I have my vector and I have a set of coordinate axes, and the idea is I want to break up this vector into its xy components. So here's what we do. I want to write this vector, the vector A here, this red one, I want to write it as the sum of this vector plus this vector. We previously learned about how you add two vectors, and you see how these two black vectors here, this one that moves along the x-axis and this one pointing along the y-axis, when you add them together, they give you this red axis, this red vector. Okay? So we're going to write this red vector as the sum of these two black ones. Now the first thing we have to do is figure out the length or the magnitude of this vector here, and then we have to figure out the magnitude of this vector here. Okay? Well, just recalling some basic trigonometry, we have a nice right triangle here. So we know that the length of this side here is 7 meters cosine 60 degrees, and the length of this side here is 7 meters sine of 60 degrees. Therefore, I can express this red vector here, vector A, as going 7 cosine 60 along the x direction plus 7 sine of 60 along the y hat direction. So I move this way, and then I move this way, and that's equivalent to this vector here. So this expression right here is what we desire. We've broken the original vector up, vector A here, we've broken it up into its x, y components. By the way, sometimes people don't use, they like to use a little shorthand notation. So instead of saying 7 cosine 60 in the x hat direction plus 7 sine of 60 in the y hat, they'll just say 7 cosine of 60 comma 7 sine of 60. Like this is the x coordinate and this is the y coordinate. That's it. We've just broken a vector up into its components. Now you might ask, why do we want to do this? Where is this going to come up? Well, as we'll see, it makes vector manipulations easier when you want to add two vectors or subtract them. Previously, the way we did it is we had to draw them out, and to add two vectors we placed them head to tail, you may recall, or to subtract two vectors we placed them tail to tail. But if we know the vectors, what their components are, it's much easier to add or subtract the vectors in terms of their components. Also, when you get into your physics class and you start analyzing problems, you'll find that breaking vectors up into their xy components simplifies the problem, because you can study what's going on in the x direction separately from what's going on in the y direction, and that simplifies the analysis. So let me give an indication of how you might add and subtract vectors if you know them in terms of their components. So here's the idea. Here's a vector A. Suppose we know it in terms of its xy components. Let's say it's 4 units in the x hat direction plus 1 unit in the y hat direction. So again, this dash vector plus this dash vector add up to the original vector. Okay, so we have our vector A. Here it is expressed in terms of its x, y components. Here it is in shorthand notation. Okay, now let's say I have a second vector, B. Here it is. In terms of its components, let's say this vector is given by 3 in the x hat direction plus 5 in the y hat direction. Okay, so I've got vector B in terms of its components. Now suppose I want to, for example, add these two vectors together. I want to add vector A plus vector B. Well, previously we've seen how to do that. You take vector A and you place it head to tail against vector B, and then you draw a line from this end all the way up to that end. And so this red arrow here, which I've labeled vector C, that is the sum of vectors A plus B. But now let's think about how we would express vector C in terms of its components. Well, if you look at this diagram here, you see that if I walk over 4 units horizontally and then an additional 3 units, that gets me to here. And in terms of how far I have to go up vertically, if I go up 1 unit and then an additional 5 units, total of 6 units, that gets me to here. So in other words, vector C has components given by 7 in the x hat direction plus 6 in the y hat direction. In other words, 4 plus 3, 7 in the x direction, and in the vertical direction, 1 plus 5, 6. So the point is, if you're told the components of a vector, the xy components, and you want to add those two vectors, you just add the x components, 4 plus 3 is 7, and then separately add the y components. Very easy. It's actually easier than just drawing out these arrows and then drawing out the connecting one. Likewise, we can also subtract two vectors. Okay, so here's vector A again, here's vector B. Previously, we've seen that if we want to subtract the two vectors, so if I want to take vector A minus B, for example, what I do is I place the two vectors tail to tail and then draw an arrow from the vector that's being subtracted off to the first vector, so from B towards A. And that red arrow that I drew there is the vector A minus B. But we can also determine what this vector C is just in terms of its components. All we have to do is take the components of A minus the components of B. So we start with the x components. 4 minus 3 is 1, and 1 minus 5 is negative 4. So in other words, this red vector C can be expressed as 1 unit in the x hat direction minus 4 units in the y hat direction. Can also multiply vectors by scalars, by numbers. We've seen that previously. So for example, if I had a vector A and I want to multiply it, for example, by 3, I would just draw that vector 3 times longer. Same direction as before, just drawn 3 times longer. But in terms of its xy components, let's say, for example, vector A has components 4 units in the x hat direction plus 1 unit in the y hat direction. Then 3 times the vector A would just be 3 times 4, 12 units in the x direction, plus 3 times 1, 3 units in the y direction. So in terms of components, multiplying a vector by a scalar is very straightforward. By the way, if you have a vector, you can break it up into its xy components. But we can reverse this. If you know the xy components of the vector, then you could draw the original vector and figure out its size and direction. So for example, let's say I know that the components of vector A are 4 units in the x-hat direction plus 3 units in the y-hat direction. So here it is. 4 x-hat plus 3 y-hat gives me vector A. Now, if I wanted to know the magnitude of vector A, I could simply use the Pythagorean theorem. 4 squared plus 3 squared square root would tell me the length of this side, namely 5. So vector A has magnitude 5. Likewise, if I want to know what angle vector A makes with the horizontal, I'll just use a bit of trig. I'll say that the tangent of this angle is equal to 3/4. Therefore, the angle is equal to the inverse tangent of 3/4. So again, the point here is, if you have a vector, you can break it up into its xy components, or if you know the xy components of a vector, you can figure out the size and the direction of the vector. Let me give you one more example of breaking vectors into components. Suppose I have a vector. Here it is in black here. That black arrow, it's got magnitude 10, and it happens to be making a 40-degree angle with the horizontal. So there it is. I've drawn a set of coordinate axes, and suppose I want to break up this vector into its xy components. So the idea here is that I want to write this black vector as the sum of two other vectors, one going along the x-axis and one going along the y-axis. In other words, these two red vectors here, when I add them together, this vector plus that one add up to the original vector. Now, let me compute the length or the magnitude of this horizontal vector. Well, by staring at this triangle, I see here that the length of this vector is 10 cosine 40 degrees. Similarly, the length of this vector is 10 sine of 40 degrees. So again, this vector plus this one adds up to the original. Therefore, I could write this original vector as negative 10 cosine 40 in the x-hat direction plus 10 sine of 40 in the y-hat direction. So if I wanted to express this original black vector here in terms of its xy components, I would write it like this. Now, there's one thing very important that I want to point out here. When you're breaking up a vector into its components, you draw it as the sum of two vectors, one parallel to the x-axis, one parallel to the y-axis. Don't forget to put your arrows here. I didn't just draw a line here and a line here. I drew an arrow here and an arrow here, because what I'm saying is that this vector plus this vector adds up to this vector. Okay? And when I wrote 10 cosine of 40 here, that represents the magnitude or the size of this red vector. Likewise, 10 sine of 40 represents the size of this vector. Magnitudes of vectors are always positive, so I always put a positive number here or here to note the magnitude of a vector. But now, when I'm writing this original black vector in terms of its xy components, notice that I put a minus sign here. That's because this black vector, how do I form it? I walk 10 cosine 40 in the negative x-hat direction. Remember, x-hat is a unit vector that points along the x-axis, so it points to the right here. But I have to walk this way, so this vector is size 10 cosine 40, but it points in the negative x-hat direction. It points to the left. And likewise, this vector here has size 10 sine of 40, and it points in the positive y direction. So I write it as 10 sine of 40 in the positive y hat. So I've just successfully broken up this vector into its x, y components. Now I want to show you something related to this, but with a little bit of a twist. Imagine if I start with the same vector. So here I've drawn that same exact vector as before. But instead of drawing the good old x, y coordinate system like I had over here, suppose I introduce a new set of coordinates, these dashed coordinates. I'll call these the x prime, y prime axes. And these new coordinate axes are tilted relative to the old one. They've been rotated by, let's say, 15 degrees. So there's 15 degrees from here to here, 15 degrees from here to here. In other words, just take these two coordinate axes and rotate them counterclockwise by 15 degrees. And that gives you these new coordinate axes, these dashed ones. Okay? So I have the original vector, and I have these new coordinate axes, x prime, y prime. And now, suppose I want to break up the original vector into not its x, y components, but rather its x prime, y prime components. Well, the philosophy is the same. I'm going to write this vector as the sum of two vectors, one that goes along the x prime axis and the other that goes along the y prime axis. So what I've drawn here in red is a vector that travels along the x prime axis and another vector that travels along the y prime axis. Just like over here, I drew one vector that traveled along the x-axis and one that traveled along the y-axis. Except this time, I want to break up the vector into its x prime, y prime components. So that's why I draw this vector along the x prime axis and this one along the y prime axis. Let me now get the lengths or the magnitudes of each of these two red vectors. Well, look at this right triangle here. And from trigonometry, we see that the length of this side is going to be, well, it's going to be 10 times cosine of, now the angle that we want is the angle from here all the way down to here. In other words, this is 40 degrees, but then there's an extra 15-degree rotation, because remember these x prime, y prime axes are rotated by 15 degrees. So there's an extra 15 degrees here, so this total angle is 55 degrees. Likewise, the length of this side here is 10 sine of 55 degrees. So to express this black vector in terms of the sum of this vector plus this one, I write it as follows. I go 10 cosine 55 in the negative x hat prime direction, and then I go 10 sine of 55 in the y hat prime direction. What you're looking at here is this black vector expressed in terms of its x prime, y prime components. Okay, now go back to here. This was that same vector. In both cases, I haven't changed this vector. It's the same exact vector, but here I've expressed it in terms of its xy components. Here it's expressed in terms of its x prime, y prime components. They are the same vector, just expressed in different coordinate systems. It's kind of like speaking different languages. You know, if we think about the word for dog, we can say it in French, we can say it in English, we can say it in Spanish. It all means the same thing. So you can think of maybe this is English, this is French, for example. Now, at this point you might be asking yourself, why on earth would we ever want to consider these tilted coordinate systems like the x prime, y prime here that I introduced? Why not just always stick with x, y coordinate systems, the usual ones that are horizontal and vertical, not tilted? Well, there's a good reason for that. They actually arise in practice all the time. And here's how. When you're analyzing a problem in physics, you want to choose a coordinate system that's natural or ideal for the problem that you're looking at. So for example, let's say I was studying a ball rolling along the ground here. Since the ball is moving this way, it's most natural to define a coordinate system like this, with the x-axis pointing in the direction that the ball's rolling and the y-axis perpendicular. That's very natural for this physical situation, this physical geometry. But suppose instead I was studying a ball rolling down a ramp. Now the ball is moving this way. It's not moving purely horizontally. It's not moving vertically. It's moving this direction. So for this problem, it's most natural to introduce a coordinate system that's tilted, that runs along the ramp, with the x-axis along the ramp and the y-axis perpendicular. This would be the natural coordinate system for this problem. This would be the natural coordinate system for this one. So depending on the physical problem that you're trying to analyze, you're going to choose your coordinate systems appropriately, and then you're going to want to break vectors up based on those coordinate systems.